Module 1, Fatigue Life Methods. The three major fatigue life methods used in design and analysis are stress life method, strain life method, and linear elastic fracture mechanics method. Linear elastic fracture mechanics method. Also known as LEFM method. These methods attempt to predict the life in number of cycles to failure. That is, these methods predict the number of cycles to failure denoted by letter capital N for a specific level of loading. Or what it means is, for a given level of loading, how many number of cycles the component can withstand without failure. This is what is found in the fatigue life methods. If the number of cycles to fatigue failure is less than 10 power 3 cycles or 1000 cycles, it's called low cycle fatigue. And if the number of cycles to fatigue failure is greater than 10 power 3, such kind of failure is known as a high cycle fatigue, denoted by HCF and LCF. So low cycle fatigue is a fatigue failure of components less than 10 power 3 number of cycles. And if the number of cycles is greater than 10 power 3, it's called high cycle fatigue or HCF. So basically these three methods are there: stress life method, strain life method, and linear elastic fracture mechanics method. So first we will see what is a stress life method. Stress life method is based on stress levels only. Is based on stress levels only. And this is the least accurate method. Out of the three methods, the stress life method is the least accurate, especially for low cycle fatigues. It's least accurate, especially for low cycle fatigue, because in low cycle fatigue the stress levels are very high that plastic deformation of the material takes place, and this is not considered in the stress life method. Therefore this method is less accurate for low cycle fatigue components, and this method is easiest to implement. For a wide range of design applications. And this method has got ample supporting data. And since this is the easiest method, this has got sufficient number of supporting data, and this method can represent high cycle fatigue adequately. High cycle fatigue adequately. Because at high cycle fatigue the stress levels are slightly less, therefore the complication does not arise. So for high cycle fatigue applications, stress life method can be used very effectively. The second method is strain life method. The The strain life method involves detailed analysis of the plastic deformation at localized regions. That is, detailed analysis of plastic deformation at localized regions. And this is good for low cycle fatigue application. This we have seen earlier. I told that in low cycle fatigue application, the stress levels are very high, that plastic deformation of the material take place. And in this stress life method, this plastic deformation was not considered. Therefore, it was least accurate for low cycle fatigue. But strain life method considers the plastic deformation that take place at the local regions. Therefore, it is good for low cycle fatigue applications. And the third one, basically the last one, is the LEFM method, or linear elastic fracture mechanics method. This is the third method, and this method assumes that a crack is already present in the material and has been detected. That is, this method assumes that a crack is already present in the material and is detected. And this method predicts the crack growth with respect to stress intensity. And this is most practical for large structure applications. For large structure applications. So these are the basically three methods which are used for predicting the fatigue life: the stress life approach, strain life method, and linear elastic fracture mechanics method. And we will be studying the stress life method in detail in this course of machine design. So in this module we will see the stress life method in detail. To determine the strength of a material to fatigue loads, specimens are subjected to repeated or varying forces as shown here. The force which is varying with respect to time, the mean value is 0, so it's tension in this phase and compression for the other half of the cycle. Similarly, for next half of the cycle is in tension, the remaining next half is the compression. This kind of a varying force, when subject to the body will fail after a number of cycles. So what we do is, we give some kind of loading which produces some kind of a fluctuating stress in the material, and we see how much number of cycles the material withstands without failure. So commonly used fatigue testing machine is fatigue testing is done in a machine called the RR Moore rotating beam machine. This is important. Rotating beam machine is the one in which the fatigue life of the component is studied. Here the rotating beam machine is shown in this figure. Here this beam is rotated at a very high speed, and a constant load is applied at the center. When a load is applied at the center, we know that this is a simply supported beam. So a bending moment is created in the beam, and a stress level is maintained by means of weight hanging from the center. In this testing, a constant bending load is applied. A constant bending load is applied, and number of revolution of a beam required for failure is recorded. For failure is recorded. So we have a set of stress values and a set of number of cycle values, that is S and N values we have. So to start with, what we do is, the first test is made at the stress level somewhat under the UTS. That is, we apply a load in this beam such that the stress in the material comes to be less than UTS, slightly less than UTS. Say we will take the first stress value as S1, and the corresponding number of cycles is recorded N1. That is, for S1, the number of cycles is N1. In the second test, the stress level is adjusted such that it is just below the first test. So we have second stress level and second number of cycle N2. Similarly, we have number of cycles, we say S10, N10. It goes to S100 and N100. Keep on doing with reducing the stress levels and see the number of cycles withstood by the body. So we get a series of values between stress and the number of cycles. Now this is plotted against each other. This is known as the SN diagram. So what is done is, we are having a number of S values and N values, stress values and the number of cycle values. This is plotted against each other. So start with, we have the stress which is slightly below the UTS value. This is the stress value, and this is the number of cycles. This is plotted in a log scale. Therefore, this is 10 raised to 3, this is 10 raised to 6. They look to be very near to each other because this is a log scale. So this is nothing but 3 and this is nothing but 6. This is a natural logarithm scale. Similarly, log scale is followed in the ordinate axis also. The stress levels are plotted in the y-axis and number of cycles of failure is plotted in the x-axis. So the first point we get here, which is stress just below the UTS, and we have a particular number of cycles. Now second test is done at the stress level slightly below the first test, that is this value, and you get another number of cycles, say here N2. So similarly you get S3 N3, S4 N4, S5 N5, S6 N6. Like that you will get all the values of stress and number of cycles. They are plotted against each other, and this figure is called the SN diagram. And this is a typical SN diagram for a ferrous alloy. So therefore, whenever we say the fatigue strength of the material, this should always be accompanied by a number of cycles. That is, if I say the strength is something like here, the strength value is here, then I should also say what is the number of cycles. So this is important. For ferrous alloys like steel, we can see a knee occurs in the diagram. And a significance of this knee or this straight line portion is that beyond this knee, that is, if the stress in the component is below this value, SC dash, the material will not fail at all. Whatever be the stress applied, the material is going to withstand infinite number of cycles. And the strength corresponding to this knee is called the endurance limit or SC dash or fatigue limit for this material. So this is a very important term, which is nothing but the endurance limit. Is nothing but SC dash, and only for this ferrous alloys we can see a particular distinct knee in the SN diagram, and the stress, if the material is stressed to a level below this SC dash, then it will undergo infinite number of cycles. Therefore, now we have a very important term called the infinite life and finite life design. So if we want to design the component for infinite life, we should make sure that the stress in the component is less than the endurance limit of the material. So this is the SN diagram of the ferrous alloy. Here we can see that I've mentioned about the knee occurring in this diagram, and the stress corresponding to this knee is called the endurance limit of the material. So there comes another important parameter called the finite life design and infinite life design. As I've mentioned, if we want to design the component for infinite life, then we should make sure that the stress in the component is always less than the endurance limit of the material. Therefore, if we have to design the component for infinite life, the parameter which we have to find out is what is the endurance limit of the material. And we should make sure that we should design the component such that the stress is less than the endurance limit value. And if it is a finite life design, then for undergoing a particular number of cycles, say here, if I want to undergo say 10 power 4 number of cycles, so it will be here in the logarithmic scale. So we have to find what is the stress corresponding to the 10 raised to 4 cycles. That will be something here. That will be this value. So if the component has to withstand 10 raised to 4 cycle, the stress coming in the member should be this value of the stress. And keep in mind that the SN diagram is plotted on a log scale. So 10 power 4 cycle means it should be 4 here. It will be 4 here. So we'll try to solve a problem regarding this infinite life design and finite life design, which will make the things clear for us. So as we have seen in the first module on a tensile stress strain diagram of a specimen, we have seen that only mild steel exhibited a well-defined yield point, and other ductile materials do not have well-defined yield point. So we had a 0.2% offset method. Similarly, for SN diagram also, only the ferrous alloys exhibit a well-defined endurance limit. Non-ferrous alloys do not have any well-defined endurance limit. So thus for ferrous alloys we have the well-defined endurance limit, and this classifies the SN diagram divides the SN diagram into two regions, finite life region and infinite life region. And the boundary of this between the finite life and infinite life is not clearly defined. Usually it is taken as 10 raised the boundary between finite life and infinite life. Boundary between finite life design and infinite life design lies the range of 10 power 6 to 10 power 7 cycles. It's not well defined, it lies in that range. So that is about the ferrous alloys. For non-ferrous alloys and aluminum alloy, the SN diagram looks something like this. So from this diagram we can see that there is no well-defined knee or well-defined turn in the SN diagram. Therefore, these materials do not exhibit any kind of endurance limit. So endurance limit is not defined for non-ferrous and the aluminum alloys. For them we have a parameter called the fatigue strength. And usually fatigue strength of these materials can be considered as the stress level corresponding to 5 into 10 power 8 cycles. Therefore, fatigue strength can be considered as the stress corresponding to 5 into 10 power 8 cycles. Let me write it clearly. 5 into 10 raised to 8 cycles. So corresponding to that number of cycles, what is the stress? That will give the fatigue strength of the material for non-ferrous and aluminum alloys alone. For ferrous alloys, we have the well-defined endurance limit. This fatigue strength concept is applied only for non-ferrous and aluminum alloys.